Hi, in this video we'll talk about the no cloning theorem. So the no cloning theorem is an interesting theorem because it puts some constraints on quantum mechanics. Typically, up till now we have said that okay, quantum mechanics has these properties called superposition and entanglement, which gives it more power than classical computation. But no cloning theorem is one which actually produces a constraint. Uh, Roughly speaking, it says that an unknown quantum state cannot be copied or cloned. Now, in classical computation, this is a fairly straightforward operation. Copying a classical bit is done quite frequently in a classical circuit. So the history of the no cloning theorem is that it was discovered actually in the 1970s, but later rediscovered in 1982 by Zurich and Wouters. And it was actually it was in response to a scheme of superluminal communication, which means faster than light communication. So let's look at the no cloning theorem in this video and its implications. Um, so let's look at the no cloning theorem. So no cloning theorem. It states that an arbitrary quantum state cannot be cloned, be copied or cloned. So what does that mean in terms of quantum computation? It means that we cannot build a circuit. So let's say we have a circuit with a unitary and we have an unknown quantum state ket psi. And let's say a reference state, let me just take it to be 0, but this could be any reference state. And so cloning circuit would effectively make a copy of this unknown state. So it will be a unitary that outputs a copy of this state at psi. So the proof of this theorem, which I'm going to do right now, is just a proof by contradiction. So supposing such a circuit or a unitary exists, then we have a U of acting on ket psi tensor 0 is equal to psi tensor psi. And let's take ket psi to be equal to alpha ket 0 plus beta ket 1. Right? Um, so if I expand this, I'll get U alpha ket 0 plus beta ket 1. This tensor with 0 is equal to, and if I just expand the right hand side, I'll get mod alpha square. So alpha square 0 ket 0 plus alpha beta 0 1 plus alpha beta 1 0 plus beta square 1 1. Right now, on the left-hand side, I'm going to use the linearity of U. So U is a linear operator. Therefore, I can write it as alpha times U acting on 0 tensor 0 plus beta times U acting on 1 tensor 0. So suppose such cloning was possible, then the right-hand side should be equal to the left-hand side. So alpha square 0 0 plus alpha beta 0 1 plus alpha beta 1 0 plus beta square 1 1. So since this is a cloning circuit, it should clone in particular the zero state and the one state also. So therefore, on the left hand side, we get this plus now in this one qubit gets cloned, so it will be 1 1. So we have this left hand side equal to the right hand side, but this is not possible since there are no cross terms on the left hand side, and this circuit is possible only for very specific states. For example, if alpha is 0 or beta is 0, then we may be able to clone it, but in general for an arbitrary quantum state, this circuit is not possible. So this circuit cannot be built, so this is not possible. Now, having said that, let's see what are, so the no cloning theorem is actually a very important theorem, and it has some very important consequences. So let's look at some consequences of the no cloning theorem. So consequences. So the first one is error correction. So as you know that in quantum computation, one of the key things is error correction because of environmental noise. Often uh, qubits decohere, and we have to have some various error correcting schemes. So one of the constraints of this scheme would be that a scheme such as, kind of copying the state of the circuit mid computation and then using that to do some error correction is not possible. So constraints, it puts a constraint on error correcting schemes. Then also in quantum cryptography, the eavesdropper is because of this no cloning theorem is unable to copy a transmitted a secret string of qubits. So eavesdropping is in a traditional sense is not possible. So eavesdropping in quantum cryptography. And also the no cloning theorem also protects the uncertainty principle in some way. Suppose you are able to make a very large copy of a unknown quantum state, and then you could use various measurement apparatus or various incompatible observables to detect or to find out what that particular quantum state is by making a large number of observations. So it protects the uncertainty principle as well. So protects uncertainty principle. And finally, as I mentioned that uh, uh, the scheme of the no cloning theorem was in response to a scheme of superluminal communication. And so, for example, if I have, let's say, so no superluminal communication, by cloning. So, for example, let's say Alice and Bob are separated by a large distance, and they share uh, a state which is maybe looks like this over square root of 2. So this is an entangled state shared by Alice and Bob. Then one scheme of superluminal communication could be that if Alice wants to transmit 0, then she measures her qubit in the Z basis. So measures qubit in Z basis. Alice. So Alice wants to transmit a 0. If Alice wants to transmit 1, then she does nothing. And Bob, on the other hand, um, what he does is that he takes uses cloning to make several copies of the state that he has at her end after, and then depending on the probability distribution of that state, he's able to distinguish between whether Alice has transmitted a 0 or 1. So suppose Alice wants to transmit a 0, and she measures her qubit, then with probability 1, Bob will either be in state 0 or state 1. Whereas if Alice does not do anything, then Bob will have, so this will be either 0 or 1 with probability 1 in this case. And then in this case, it will be probability half of having a 0 or a 1. So if Bob is able to make several copies of this state that he has, then he'll be able to distinguish between the two cases, and this will lead to superluminary communication. So the no cloning theorem protects this from happening.